Okay, so now we are going to discuss MRI, magnetic resonance in energy. Now, first of all, every nucleus with odd number of protons behave like a tiny magnet. It's similar to atoms with uneven number of electrons, but now our focus is on nuclei. So what happened here is, if you have two protons, one spins clockwise, one spins anti-clockwise, they will cancel each other, so there won't be any net magnetic field. If you have three protons, one clockwise, one anti-clockwise, another one is anti-clockwise again, there will be a net magnetic field. So therefore, nuclei with uneven numbers of protons behave like a tiny magnet. But at first, all these tiny magnets, they are all in random direction. As such, there won't be any net magnetic field. Okay? So what we do here is we impose a strong magnetic field to align this tiny magnet. So we impose a strong and uniform magnetic field, okay, to align the tiny magnet. So the tiny magnet, they will follow the direction of strong magnetic field. Okay. And when they align themselves according to the strong magnetic field, they are not just aligned and then stop. They will be spinning around the axis of the strong magnetic field. So this is a strong magnetic field. And all these tiny magnets, they will be spinning around, okay, the axis of external magnetic field. And this motion is called precession. And the frequency of precession is called Larmor frequency. So Larmor frequency is actually the frequency of resonance. Okay? And this Larmor frequency depends on the value of magnetic field where the nucleus is located. The stronger the magnetic field, the faster, as if the higher the frequency of this precession. The next one is it depends on nucleus, which is the same throughout because we're talking about hydrogen. Because in our body, nuclei with odd numbers of protons, we use hydrogen because we have abundance of hydrogen in our body. So the nucleus wise is the same, but magnetic field, let's say normally we will apply probably 1 to 1.5 Tesla. Okay, so that's the magnetic field. So align them, precess at Larmor frequency. So if you apply 1.5 Tesla, the Larmor frequency is about 63 megahertz. So 63 megahertz is actually in RF region. Okay, so what we do is we actually impose RF pulse into the body. Okay, so to disturb the equilibrium. And all these tiny magnets, they will start to be precessing with maximum amplitude about the axis. So throughout the process, okay, so it's chaotic. Okay? So throughout the process, the strong magnetic field is still there. Okay, so resonance occurs because the RF pulse that we send is in the same frequency as the Larmor frequency of precessing nuclei, which is hydrogen. So these nuclei, they will precess with the largest amplitude. And at the end of this RF pulse, this the motion will actually goes back to equilibrium position. Okay, so from chaotic state, go back to equilibrium position. And by doing so, energy absorbed just now is re-emitted. And the energy re-emitted after all these nuclei have gone back to the equilibrium state is known as MRI signals. Okay, and MRI signals, we have the intensity, like how strong the signal, and intensity of MRI signals will tell us the density of hydrogen. Okay, that means in certain area we have fat, we have watery tissue, there are many these hydrogen atoms, and therefore the intensity of MRI signal is strong, because imagine one hydrogen nucleus emit 1 joule, for example. If you have 100, then you have 100 joule. Okay, so we have more hydrogen atom in certain region, then the intensity is larger. And we can actually investigate the frequency of signal. The frequency of signal will be the same, which is still 63 megahertz. Okay, because that is actually the frequency of energy it absorbs. So afterwards, it will re-emit the same frequency of energy. And we can talk about the time. The time taken for the chaotic state to the equilibrium state. So this time is affected by what is the neighboring these atoms around hydrogen. So it can tell us, the time can actually tell us what is the tissue composition around this hydrogen. Because different composition, you have different time taken to go back to the equilibrium. So we call it relaxation time. Time for it to relax, go back to the equilibrium state. Now the question here is, the energy is emitted, but the energy is emitted throughout the body. So how do we know which part of the body the signal is coming from? So we must find a way. That's why we impose a magnetic gradient on top of this uniform magnetic field. Now, let's say, for example, we want to get the MRI image for our brain. So what we do is we will impose the external strong and uniform magnetic field. (1.5 Tesla). And on top of it, we actually impose a magnetic gradient to differentiate the body. So you can apply the uniform magnetic field along x direction. That means you actually divide our brain or head into these slides. Okay, like for example, these slides could be from, let's say, -5 millitesla all the way to +5 millitesla. So that's a gradient. So here's -5, -5, -4, -3, -2, -1, 0, for example. And then +1 milli, +2 milli, +3 milli, and so on all the way. So we divide it into many slices. So now every slice of the brain will have slightly different magnetic field. Okay, it's like 1.5 plus -5 milli, 1.5 plus -4, -3, 0, and so on. So only one slice will have 1.5 plus 0 millitesla, which is 1.5. So that means only one slice of body will still have a magnetic field 1.5 Tesla, and therefore the resonance frequency is 63. So the rest of the slices will have slightly different resonance frequency or Raman frequency. So therefore, when 63 megahertz of RA pulse is sent into the body, not all part of the body will resonate. Only 1.5 plus 0, only one slice will resonate and absorb the energy, become chaotic, and goes back to the equilibrium position by emitting MRI signal. So then, by collecting this MRI signal, we analyze these three different factors. We know that this image that we are going to construct belongs to this particular location. Okay, so by applying different frequency, we can actually locate the nuclei which emit the energy. So we construct the image for this particular slice. So afterwards, you can actually shift it. Okay, you shift the magnetic field either up or down. Okay, so that now the other slice will have 1.5 Tesla. Then we also construct the image from this particular slice. So the process actually continues until you get all the slices being involved in resonance, and you have collected the data. The computer will actually process it to construct the image for every slice. And afterwards, what we do is we can actually change. Okay, so what we do is just now we actually differentiate the body horizontally, like x direction. So now you can actually divide it into like vertical slides. Okay, so same thing, -5 millitesla, -4, -3, -2, -1, 0, +1 milli, 2 milli, 3 milli, 4 milli, and +5 milli. So now the magnetic gradient is imposed along y direction. Just now it's x, now it's y. So you can actually change the magnetic field along x, okay, y, and z direction. Okay, so that means you can actually divide the slices not just x direction, y direction, but also cut it across z direction. So by doing so, we can actually construct our image to a very detailed or high resolution of quality as we collect the data for every single slices in all different 3 directions. That's why MRI, this imaging, it takes a long time, because imagine if you want to get a high resolution of image, you have to collect the data from all 3 directions before you can construct a high resolution image. It's like, for example, if you want to take an image for your knee, it takes about 30 minutes, provided you're not moving. Once you're moving, then the magnetic gradient will be, it will affect the image, because the location changes. So then the process has to be repeated and doing again to get the image. So that's all for the explanation on MRI.